Hello, my name is Cameron Sabet, and this is Cutting to the Case. And today we're joined by Dr. Françoise Combes, one of the world's leading astrophysicists and the president of the French Academy of Sciences, one of the oldest and most prestigious scientific institutions in the world. Professor Emeritus at the Collège de France and astrophysicist at the Paris Observatory, Dr. Combes has spent 5 decades investigating how galaxies form, evolve, collide, feed their central black holes, and acquire their unseen mass. Her work combines astronomical observations with numerical simulations, and she was the first to identify the mechanism by which vertical resonances of stellar bars can produce bulges in spiral galaxies. She also pioneered the use of molecular absorption systems in front of distant quasars to test whether fundamental physical constants have changed over cosmic time. Dr. Combes has received the 2020 CNRS Gold Medal, France's highest scientific distinction, and the 2021 L'Oréal UNESCO for Women in Science International Award. A member of the French Academy of Sciences since 2004, she became its president for 2025 to 2026, only the second woman to lead the Academy since its founding in 1666. On Cutting to the Case, we discuss dark matter, modified gravity, supermassive black holes, the birth and death of galaxies, what the earliest universe may reveal, and what 5 decades at the frontier of astrophysics have taught her about how science advances. Thank you so much for joining us today.
Yeah, thank you very much for all this complete biography.
Absolutely. There is no amount that I could share that would not make it complete. There's obviously much more that I've left out for the sake of time. Now, going all the way back to the 1970s, you began your doctoral work on the dynamics and structure of galaxies. What did astronomers fundamentally misunderstand about galaxies when you entered the field that we now take for granted?
Yes, when we entered the field, there was still this dark matter problem, which is still with us now, but we have understood a lot about that. We have not discovered what the particles are, but we have discovered what they are not. So we have eliminated a lot of possibilities. And this is
Hmm.
maybe not very visible, but it is very interesting because we have eliminated theories, a lot of theories that have been deployed, and also tried to detect some particles. And there was WIMPs candidates, for instance, that were supersymmetric particles, and we discovered that there's no supersymmetry. So
Hmm.
a lot of things have been eliminated, rolled out. So we have progressed a lot, but now it is true that we begin to be short of new candidates for these particles because there is nothing detected in detectors under the mountains. Have big detectors. At the beginning, it was kilograms of detector. Now we have tons, 8 tons of xenon, liquid xenon, and there is nothing. And also in the CERN, in the accelerator of particle, we were expecting finding when the protons arrive with a lot of energy, and they are arriving with 100,000 times of the mass energy of the proton. We were expecting some particles arriving there, and there's none. So one of the theory that is most stimulating now and attractive is the modified gravity, because well, this problem of missing matter, it can be solved two ways. In fact, either you take the normal Newton and Einstein gravity, and then you have to add a lot of dark matter to explain the rotation of galaxies or the equilibrium of galaxy clusters. But if not, if there is no particles, then you can modify the law of gravity. So it's much more difficult because Einstein theory of gravity is very solid, and it's not a force like electromagnetic force, it's a deformation of space. So it's very heavy to have a covariant particle, relativistic, with a deformation in a tensor-like curvature and so on. But a lot of people are working on that, and maybe it will be the solution. We don't know, in fact. So people are searching in both ways, either still trying to find particles or modifying gravity. And there are many theories to modify gravity. There are some which works for galaxies or for cosmology, but I think in the future something must arrive.
Mhm. Yes, and arrive it will, hopefully. And You were also the first to show through numerical simulations how vertical resonances in stellar bars can build boxy or peanut-shaped galactic bulges. What gave you the intuition to look for that mechanism?
Yes, it was really serendipitous, in fact, because we were trying to find why, in theory, in fact, there was no bars, you know. Of course, when you look at galaxies, you find two-thirds of them are barred. But bar is very strong perturbation, and the theory was only perturbation. You know, it's not possible to compute when it is non-linear. So it was only spiral, very small perturbation of spiral structure. It was understood. But then when you make computation, and people at the beginning making 2D because galaxies are very thin disk, so to save time, computing time, they make a 2D picture of a galaxy, and then they find bars, bar instability. Even if you begin with a galaxy which is completely homogeneous, after a while there is a bar which comes in your galaxy because of self gravity, only gravity is the main force. So we wanted to know why there are so many bars, and in fact, there are some galaxies that are not barred in observations. So we wanted to get rid of the bar. So we said, well, maybe if we put a third dimension, of course, it's very expensive to compute that, but we tried just to make get rid of the bar. But then we saw that the bar there was resonance, and then we find the bulges and the very thick bulge with a peanut shape like. I say, well, there are some galaxies that look like peanut. There is even the peanut galaxy, a prototype. And then nobody interpreted that, why there was peanut shape in the bulges of galaxies. And then we discovered that it was serendipitous. And then we explained because of the resonance of the orbits and so on. And then there was a window open. A lot of people work on these bulges. It's a way to form bulges of galaxy, which are like very thick things in the center of galaxies and different from the thin disk. So that was a very, very interesting discovery.
Hmm, hmm. Yes, and when we look at a spiral galaxy and see the seemingly stable, beautiful structure, how much of that appearance is actually the product of continual instability and redistribution of matter?
Yes, it's not stable at all. In fact, when you look at the simulations on the computer, the spiral is coming there and disappears and comes back again. So it's like a wave. When you throw a stone on the lake, you find a wave, and there's a wave, and if you have to to put the other stone to have more waves, but it's like that because the waves are dissipating, and then they are not long-lived. The bar is more long-lived, and the bar can entrain some spiral structure, but then you need a lot of gas arriving. And we think that gas is arriving continuously from the cosmic filaments. The
Hmm,
galaxies are not isolated. After a while, they consume their gas in star formation, but then they are constantly refueled by gas, and then another spiral forms and so on. So it's dynamic, it's not stable at all.
hmm. And our own Milky Way has a bar. What is that
Mhm.
bar doing to our galaxy right now, and how different might the Milky Way look several billion years from now because of it?
Yes, in fact, it's very common. I told you in spiral galaxy, two-thirds are barred, so we are in the majority of galaxies. And we think that bars come and go sometimes. It takes a giga year, a billion years to form and then also to disappear. But what it makes is that it gather all the gas to the center to build the bulge, in fact. And if there was no bar, if there is an axisymmetric disk, then you have stars and gas rotating without losing their angular momentum. So you need to exchange angular momentum with the outer parts, and the bar does that. So you need something which make a torques, in fact. If there is no torque, then the gas will continue and you will not form the galaxies. You will not concentrate the mass. And the bar is concentrating the mass and forming a little bulge, which has a peanut shape, in fact. So it's exactly what we discover in the computer.
Hmm. And you've worked extensively also on galaxy interactions. When two galaxies collide, what determines whether that encounter triggers enormous star formation, feeds a black hole, or instead suppresses future star formation?
Yes, and galaxies are frequently interacting because, in fact, they are formed in filaments. They are not in voids, so they are not uniformly distributed in space. They are gathered in filaments. So in filaments, they come together and then they have tidal interaction. Tidal interaction means that they deform their bodies, in fact, and then the energy of the orbital motion one around the other is lost. Sorry, and then you fuel the gas is fueling the center. In each galaxy, you have a supermassive black hole. We know that from the beginning of Hubble Space Telescope when we were able to see the motion, very quick motion of stars near the center of galaxies. Then you can measure that there is a black hole here. So every galaxy has a very strong black hole in the center. And when there is interaction of galaxies, of course, all the gas from one galaxy to the other uh, goes to the center. There is very chaotic deformation and shocks also gas to the other. So shocks make the gas lose energy and come to the center. So you can refuel the black hole in the center and make some activity because when the black hole is fed by gas, then you can have a quasar. The quasar is very energetic phenomenon. The gas lose its very strong gravity. In the black holes, gravity is very, very strong. So it emits in UV, in X-rays and so on, very energetically. And then you can see the quasar at the beginning of the universe, very far away.
Hmm. And you also kind of you've studied molecular gas because it's effectively the raw material for stars. What's the biggest thing we still don't understand about how cold gas becomes a galaxy full of stars?
Mhm. Well, the coal gas, when I began to observe that, it was in the 80s, and it was a surprise because in the interstellar medium, you have a very, very diffuse gas. It's a few particles per cubic centimeter, while in the gas of this room, for instance, it's 10 to 26 particles per cubic centimeter. So you see, it's really a void, in fact, more empty than we can do in the Earth, in fact. So in this kind of very diffuse and void, we were expecting no molecule formation because molecule you have to have atoms that collide together, and if they are separate, they never collide and you cannot
Yes.
form molecules. But we were surprised in the 80s to find so many molecules. In fact, we discovered a lot, and I participated to this hunt to molecules. That is, there was organic molecules. We discovered alcohol, ethylic alcohol, or methanol, or organic molecule like acetone, for instance, that was discovered. A lot of very heavy molecules like benzene, and all organic molecules are already there, and maybe amino acids like a glycine, in fact, uh, all what are the bricks to form proteins, for instance, are there in the interstellar space. So we are very surprised to see that. And of course, we wanted to know how much molecules there are. And for that, of course, the main component is hydrogen in the universe. So we thought that the molecule of hydrogen, H2, was there. But H2, when it is very cold, and interstellar medium is very, very cold, is 10 degrees Kelvin, so minus 270 Celsius. So in these very cold things, the molecule H2 does not radiate because it's symmetric and has no dipole to rotate. So we have to trace by another molecule. The most abundant is CO, monoxide of carbon, which is very toxic in Earth, but here in space you can observe it. And it is by CO that we can make the map of the whole galaxy. And we try to make the map, and it's very interesting because then we see the spiral structure and we see where the stars, the new stars, are formed. For instance, in the Milky Way, our own galaxy, there are about two or three stars per year forming in the spiral structure. So it's very interesting to map the molecular gas in many galaxies, and until we can measure all these molecules until the Big Bang. In fact, we can look back in time and go to the first galaxies in the universe.
Wow. Wow. And I wanted to also kind of move toward the dark matter research as well, because this is fascinating. Um, you've you've spent decades searching directly for dark matter particles without a definitive detection. At what point should repeated non-detection actually change the dominant paradigm?
Yes, because in fact we were expecting, and now we have orders of magnitude. At the beginning, when it began 30 or 40 years ago, uh, we we're expecting a cross section that is a probability for a dark matter hitting a nucleus of the detector to make a recoil. In fact, so is there an interaction between dark matter and any nucleus? And there was some probability, and then this probability will have 40 orders of magnitude less than what they expected. So we have made a lot of progress, and we think that now we'll never detect it because in the tunnels now in Grand Sasso, Mont Blanc, and so on, we detect only neutrinos. Neutrinos are very elusive particles which have a small mass, but it's too small to measure. In fact, we know that it is very, very small. And a neutrino can cross the Earth without being stopped. So it's a very, very small cross section. And now we begin to detect neutrinos in these detectors of 8 tons of liquid xenon in the under the mountain. So it is a telescope to neutrinos, but not to dark matter. We will not be able to detect dark matter anymore because we have other particles. We can be detected and will saturate the detector at some point.
Wow.
So we have to stop at some point.
Yes. Yes. And if you had to assign probabilities today, how much would you put on dark matter being a new particle versus some modification of gravity?
This is very difficult question, and I prefer not to answer because I'm sure that would be wrong half of the time. But we work on both, so we are sure that we will win at the end. So
Yes.
we are working on the modified gravity. It's very difficult because there are many theories that when you develop very deeply, you find that there is a ghost, like a negative mass somewhere or whatever, some impossibilities. So there are some MOND, like Milgram devised in 1983. This is the best for the moment. So we are writing a white paper on MOND, what is going to happen in the future, to know in which direction we must go to solve all the problems. And there are still some problems. And at least it is a theory that solved the most of the problems, but there are still remaining some. So it's not, I'm not sure that it will work.
Hmm.
So we try to solve the problem, and but there are many more people working on the standard called dark matter because at least it works to form galaxies and to explain the fossil radiation of the Big Bang and so on. But there are no particles detected, so there's a big problem that there's no particles. So they try to forget about that, but it is
Yes.
the most problem, the most important problem, like an elephant in the room, in fact.
Yes. Knowing that it's
So
there. Yes.
exactly.
And
But there is also problems of the standard model in the galactic scale. In fact, we don't find the missing satellites. They predict a lot of satellites. We don't find it, and we predict also a cusp of dark matter in the center of the galaxy, and there is none. So also the dark matter standard theory has a lot of problems.
yes. Yes. And you and Daniel Fenninger explored whether
Vinegar.
some missing baryonic matter could exist as extremely cold molecular gas. How much
Mhm.
room remains today for ordinary matter hiding in forms that are simply difficult for us to observe?
Yes, a lot, because at least half of the baryons are not identified yet. You know, in galaxies, what is visible is 6% of the baryons.
Hmm.
We have also in galaxy clusters a lot of gas, hot gas, millions of degrees that constitute 10 times more mass than the galaxies in galaxy clusters. But galaxy clusters are a tiny part of the universe. So there is only 4% of the baryons in this very hot gas. So now we have to look at filaments. So most of the baryons are not in galaxies. That's what we find. So we have filaments, cosmic filaments, and we think that these filaments are very diffuse. So we have not been able to detect emission from these baryons. They are not emitting enough light. So we detect them in absorption. But in absorption, it has to be a line like the hydrogen, natural hydrogen line, but most of the gas is ionized. So we detect some lines, Lyman alpha line, but we have to multiply by 10,000 to find the relay abundance of this gas in filaments.
Mm.
Maybe it's 30%, but with uncertainty. And then there is a lot of gas which can be warm or hot, not cold enough that we have to detect it in absorption, or not warm enough that we'll detect in X-ray emission. So just an intermediate temperature where we don't detect it. Maybe there is 30% in this, and 50% of all baryons, we don't know where they are. So there is a lot of space for dark baryons
Yes. And
still.
of course, of course. And could we conceivably reach the end of the century still knowing from gravity that dark matter exists, but still having absolutely no idea what it is?
Maybe not, I don't know. But we are now with another problems, which is dark energy. We know that in 1998, we discovered that 70% of the universe was in dark energy. And I think dark energy will be solved before dark matter,
Hmm.
because dark energy is something which is constant all over the universe, and it plays the role of a cosmological constant, like Einstein introduced. And then he said that since there was an expansion of the universe, you don't need this constant, because it was a constant he introduced to make a universe static at the in 1917, where we had not yet discovered the Big Bang and the expansion of the universe. So universe should have been static in his mind. But now we have discovered that there is something like that, and we have sent a satellite, Euclid. Europe has sent Euclid in 2023 to
Mhm.
observe during 5 years uh, billions of galaxies at every epoch, so that we know exactly the size of the universe at any epoch. So we'll know if there is a constant, cosmological constant, or a quintessence, that is another element which is related to dark energy. And this, I think, in 10 years from now, we'll know that about that. So at least we'll know if there is a fifth element or if there is a cosmological constant, as we think now. So this will be a mystery that we'll solve before the dark matter, because dark matter, it's 50 years that we are searching for, and I think it will not be solved in the 10 years now, from now.
Wow.
It's impossible.
Yes, yes, it certainly makes sense. And this is kind of a tangential question, but still related to the discoveries, in that there are ongoing questions about how the fields of science will advance following the application of artificial intelligence. And I'm curious, with, theoretical mathematics and astrophysics, will we reach a point at which we will be able to offload a lot of the cognitive burden of finding scientific discoveries onto general artificial intelligence, which can reiterate and solve problems almost instantaneously? Or is there a role for humans in the future?
Yes, it's a very good question, because now we are using, astronomers are using artificial intelligence for a while, because, when you observe the billions of galaxies, you cannot do that by yourself. You
Mhm.
cannot see where they are. In fact, even in an image, you need artificial intelligence to know and tell us where is the galaxy, because there's like points, and they are everywhere, but it's very difficult to detect millions or billions of galaxies. So we are used to find that, but we control them. In fact, they don't discover anything. They help us to go faster and to go to search, for instance, in the literature, what is known, why it will take hours to read every paper to know exactly a question, an answer to the question. So it's very, very helpful, but it cannot discover anything. For instance, we are building telescopes. They cannot build telescopes. And when we observe, they cannot invent what we are going to observe because it's not in the literature. What the AI does is just to read the literature and to make a compendium of all what is known. So sometimes gathering all this makes something new appearing, but it's from the literature. And if we are searching for something that is not known, we build telescope for that and we observe the universe. They cannot do that. So I think we need human at least to discover new things.
Hmm.
But AI, of course, it's a help. It is necessary because we cannot reduce what we see from the telescopes if there is millions of things without AI. Because, for instance, there is also this telescope Vera Rubin that is observing now and making a movie of the sky. Every 3 days, he observes all the sky, and every night there is 7 million alerts for variable things, supernovae, asteroids, and so on. So you need AI to make a sorting of all these millions per day and to say what is interesting to this telescope to make follow-up of this supernovae, for instance, and so on. So we need AI, but it will never replace human,
Hmm.
fortunately.
Thank you for that insight. That's fascinating. And you also, I wanted to bring this back to molecular absorption as well. You pioneered using molecular absorption in front of distant quasars to constrain whether fundamental constants change over cosmic time. How can molecules billions of light years away tell us whether the laws of physics themselves have remained constant?
Yes, because when you have different molecules, very different, the frequency of the between two levels, it's quantum, so it's quantified. So you have two levels, and you have a frequency of light coming from one level to the other. And this frequency depends if it is a rotation molecule, if it is a hyperfine structure between magnetic levels or whatever. And it depends on the fundamental constant. It depends on the velocity of light and of the magnetic moment of the proton, of the neutron, and so on, and the ratio of the mass of electron to proton. All these are fundamental constants and depends also on the gravity constant, because if you change the velocity of light, for instance, you are obliged to change the gravity constant also. And people try to think that maybe all this mystery, dark matter, and so on, could come from another theory where you change this fundamental constant. So we wanted to know if they are changing with space and time. So space, so we have looked at the Milky Way and compare the frequency of molecules for the same region, the same cloud, and if the constant were varying, you will have a different ratio between the two frequencies. So you will not see at the same place in the spectrum. And the telescope can make you look back in time because, of course, you see light that has come from a galaxy 12 billion years ago. So the light has made 12 billion years to come to you. So you are looking back in time. And then we can compare the frequency of the molecules coming from the same region. And if the fundamental constant will have changed, in fact, you will find something different and will never find something different. So all in space and time, the fundamental constants are constant.
Hmm. Thank you for that. That's fascinating. And I wanted to also get into as well the French Academy of Sciences. This institution was founded in 1666 under Louis
Mhm.
XIV. And when you sit in an institution that's existed through Newtonian physics, relativity, quantum mechanics, and modern cosmology, What do you see as its purpose in 2026?
Yes, it's true that the purpose is different, but in when Louis XIV built this, it was to have an expertise from the scientists because of navigation. Navigation at the epoch was to look at the space, the sun, longitude, and the boats. In fact, knew where they were when there was no Earth around. They need to know the sun, the position of the sun, and so on. So this was to have an expertise in astronomy
Hmm.
at the beginning, but now it's the same. We have a lot more expertise, but they need expertise in computer science, in intelligence, artificial intelligence, for instance, in climate, in biology, to have the modify organism, or in energy, nuclear energy, climate, biodiversity, and so on. So there are a lot of questions of science and society that they want the expertise of scientists to know in which direction they can take a decision. So it's about the same kind of goal
Hmm.
that we are here. So we answer the questions of the government. We make a report. We make a very deep study of a question, and then we write 30 pages, and we exchange for the media also, and we have also other missions. We are also fostering science. For instance, we give 80 awards to scientists of the country, but also internationally, we meet every year to the seven S7, the G7 countries, and also S20. So we exchange with the other academies to special topic about climate, about the satellites, constellation of satellites, for instance, and so on. So we have several missions also for education and also diffusion of science. So we have a lot of activities, in fact,
Wow.
modern activities.
Yes, yes. And after 5 decades studying a universe in which roughly 95% of the cosmic energy budget is attributed to things we still don't fundamentally understand, has science made the universe feel more comprehensible to you or more mysterious?
Both, in fact, because last century we did not know that we did not know. So that we thought that it was more simple, but now the more deeper we come and the more mysterious it begins, in fact. But we have learned a lot because this we the galaxies were not known 100 years ago. They knew only the cosmology was only the solar system and then the Milky Way. Milky Way was all our universe in 1920. They
Hmm.
began a debate. Are there some other galaxies? Now we know 2,000 billions of galaxies. So we have made a lot of progress in 1 century. And last century, we discovered this dark energy. We did not know that. Now, of course, there are more mysteries, but we know a lot more. And we are even changing the law of gravity. So it's fundamental physics that we are discovering, and we didn't know some decades ago. So I think it's exciting, and we are learning a lot, even if there are still a lot of mystery in front of us.
Yes, yes. And I wanted to also get to one of the most extraordinary aspects of your career so far. You're only the second woman to lead the academy in its roughly 360-year history. When you began your career at the Normale Supérieure in the 1970s, could you have imagined eventually becoming president?
No, 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 not at all. It was not in my ambition. So even I did not know a lot of the academy anyway. But it's true that we have made a lot of progress these last years because, even Marie Curie could not enter the academy. They were completely men only. And even her daughter, Irene Joliot-Curie, with Nobel Prizes, never entered. They had to wait 1979 for the first woman elected to Academy of Science. So it means that we have made a lot of progress because when I entered, it was only 6% of women. Now it's 20%, and we are increasing. So we hope to reach the ratio that we are in science. In STEM science, there is 35% of women. So very soon at the academy, we'll reach the 35%. We have not to have more, of course, because that will be discrimination, but we are very progressing a lot, and I think now the ambience in the academy is much better.
Hmm. Yes. Yes. And then in 2025, for the first time in the Academy's history, women constitute a majority of women constituted a majority of the elected class. Does that feel like a genuine inflection point in French science, or is there a still substantial gap between representation and equality at the highest levels?
Yes, yes, there is still some gaps. Of course, this turning point. We think that we are making a lot of progress, but it depends on the topic. And biology, for instance, there's a lot of women, even more women than the men. And in maths is more difficult, and even computer science is very difficult. Although at the beginning of computer science there were more women than men, and it reversed. So it's never finished. In fact, you have to battle again and again because it seems positive and then it's come back and it's positive, and we have to be very vigilant to keep equality. In fact, so we think that it's make a lot of progress in the recent years, but we have to keep the effort.
Yes, and are there specific programs or things you'd like to um, share on this podcast that the French Academy of Sciences is doing to kind of improve this equality or continue advancing women in science?
Mhm. Yes, we are trying, for instance, for every election, we elect 20 people every year. We try to, for each position, we have at least one-fourth should be women. At least can be half, but 25% minimum. And this has bring a lot of women because people had to find these women first. Because when you think to candidates, people have a tendency to find only men. So we have to search for them, and we find them, and they are very competing. So they are elected. So it's very nice to have put this. Of course, there is no quota. We don't impose quota, but only to find at least 25% within the candidates has made a lot of difference. When I also am very happy that we participate to this proposal to put 72 names of scientific women in the Eiffel Tower. There was only 72 men at the first floor written in golden letters. And now, this year, we have made 72 women that will be put on the just above the 72 men, so that all the tourists and all the young people, young women, could find this equality between men and women, even in the Eiffel Tower, which is very symbolic. So I think this is engaging and encouraging young women to choose science.
Yes, absolutely. The recognition is very important, and what a wonderful thing to do. And France has an extraordinary tradition in mathematics and theoretical science. Is there something structurally different about the French scientific system that the United States and other countries could learn from, or vice versa, something that France couldn't instead learn from them? Or
Yes, in fact, in the past, Georges Charpak, the Nobel Prize, he went to the States and he found that we had not an education in French as practical as in the States. And he invented la main à la pâte, which is hands-on, and he make a revolution in the education at the primary school, but also at the high school. So the academy has continued his action. There's 30 years of La Main à la Pâte, hands-on, and we think that we copied this from the States. But in mathematics, I don't know, it's just a tradition that there are a very strong school of math. That's true. And the abstraction among, so we are more in abstraction, and the States were more in hands-on, so experimental. So we learn from both.
yes,
It's
absolutely.
complementary.
Yes, yes. And I wanted to also discuss computing power, and specifically, you started doing numerical astrophysics when computing power was almost unimaginably primitive by today's standards. Has the greater computing power that modern science has created fundamentally changed how astrophysicists think, or has it mainly allowed us to test ideas we already had?
Oh, yes, it has changed a lot because now we can have billions of particles in the simulation. We can reproduce the universe. So we can test, in fact, our theories, in fact, about dark matter, about also the baryonic physics, that is, how much you form stars from the gas. And it can change a lot, in fact, because what we see are only the stars and the gas. We don't see the dark matter at all. So how galaxies form, we have to put all this we know about star forming and all these feedback processes, because each time you form a star, there is a supernovae that push the gas out, so you don't you moderate your efficiency to form stars. The same for the quasar and the black holes. In fact, in the center, you have a feedback. When you fuel the black hole, then there is a lot of gas that is ejected like that. So all this you have to simulate that. You cannot put just by theory very small perturbation. It's not completely non-linear. You have to simulate that, and the recent computers has made a lot for us to understand how it is evolving. Yes, a lot.
Yes, yes. And do you think that with simulations containing billions of particles and increasingly sophisticated physics, is there a danger that simulations become so complicated that scientists can't reproduce the universe without actually, or they can reproduce the universe without actually understanding why it behaves as it does?
No, no, we can superficially, but still, even when we make a galaxy, there is so many orders of magnitude in scales that even for if you want to simulate the whole universe, then you have to put a lot of physics by hand because you cannot form stars. It's at scale much lower than your grid scale, your resolution. So everything you know that you are simplifying a lot of things, and you have to control all these physical processes. You cannot at all simulate all the universe in all the details because you cannot simulate all atoms, of course. But
Yes,
it is
yes,
only a particle in the simulation is already a group of stars. Million of stars is one particle. So
of
it's
course.
always a simplification, and of course, you control that yourself. Of course, you can find what you're expecting because you're pushing in one sense, but there are so many people simulating that they can contradict themselves, and then we have to understand why.
Yes. Yes. And I wanted to, obviously, I'd like to respect your time here. Thank you so much for joining us today. Do you have any words of wisdom or advice for the audience of early career scholars and scientists and physicians who are eager to leave an impact on the world?
Yes, I think those who want to come to science, I can encourage them if they have vocation because it's really a satisfying profession, especially for the young girls. We always, by stereotypes, they think that science is not done for them because all these they have heard that the mathematics and physics is better for males and female or whatever. It's not true. And if they are fascinating by this, they should persist and go to their dreams, and it will come true.
Thank you very much. What an inspiring approach, and I it's so exciting to see everything that's going on in France and learning from your your scientific institutions, and thank you so much for all that you do.
Thank you.
Yes.
Thank you.
So this is Cameron Sabet from Cutting to the Case, and we're signing off. Thank you.